Ladies and gentlemen, boys and girls, welcome back to Transparent Physics. In this lesson, we're going to start a new series on energy, work, and power. And our first episode is going to be a discussion of energy, a word that we use in a lot of different contexts in everyday language, but has a very specific set of definitions in physics. By the time you're done with this lesson, we will have defined energy, again specifically in the context of its use in physics. We're going to introduce the idea of kinetic energy, and we'll show you its formula. And we'll introduce the idea of potential energy and a formula for that as well. The actual calculations for kinetic and potential energy are going to come in future episodes. For now, we're just going to introduce the main ideas. Okay, so what is energy? Energy is probably one of the physics terms that has the broadest use outside of physics. It has a lot of connotations, a lot of definitions. So we're going to definitely narrow it down when we're talking about physics. But even though we're narrowing it down, that doesn't necessarily mean that it's a very small footprint in physics, or that it's necessarily easily defined. And we're going to come up with two different ways to think about it, each of which will develop further as the series goes on. So when I teach about energy in my introductory physics classes, I will usually introduce it in two ways, sort of simultaneously. First of all, we talk about energy as the ability to cause change. Now, this is a sort of a feel-good definition here. It is a little bit vague, but it's a good place to hang your hat to start. Changing, however, can mean a lot of different things in the context of physics. Introductory physics-wise might be changing the position, changing the state or status of an object, maybe bending it, crushing it, etc. So there's a lot of ways that this can come into play. Maybe it's a little broad to be terribly helpful, but it's, I think, a good context to sort of think about energy within. Another way to look at energy is maybe a more analytical definition, and energy is the ability to do work. Work is another term that we're going to get into in this series. Another word that obviously has bajillions of implications outside of physics. Inside of physics, it has a pretty narrow lane that it drives down. And we're going to need to understand what work is first before we can really appreciate this definition. So we're going to leave that for a future lesson. You ever go on Netflix looking to start a new series, and you check first how many seasons the show was? Because you're like, oh, if there's a lot of seasons, that means if I like it, there's a lot to watch. Well, there are a lot of seasons of energy, as they say. We are going to be focusing on an extremely narrow band of energy in this course, but there are so many different ways that it comes into play. So definitely lots more to learn if you enjoy talking about energy. Specifically in this series, we're going to be focusing on mechanical energy. It's a great place to start: speed up, slow down, lift, drop, etc. The action of forces on physical objects and seeing how that affects their ability to cause change. Fast and Furious would not be able to exist without mechanical energy. Next up is sound. There is energy associated with sound. This GIF shows a crystal glass being shattered from sound vibrations. So that's definitely an ability to cause change. Chemical energy is an extraordinarily broad topic, dealing with the interactions of molecules and atoms, changing their nature mostly through the action of their outer electrons. If you want to learn more about chemical energy, I recommend you visit Guillotine Chemistry for all kinds of great information on chemical energy. Electrical energy is a little more in the purview of traditional physics and the motion and action of charges, and so there's a lot to that as well. And if you continue your study in physics, you will get to this eventually. Radiant energy is the transfer of energy via radiation. The most stereotypical version of that, we would imagine, is light. But there's a lot of other ways that we can transfer energy using electromagnetic radiation. Next up is thermal energy. Again, this tends to drift a little bit into the world of chemistry as well, with thermodynamics and things like that. But energy associated with the motion of particles. Temperature itself is really just an indication of how fast the particles are moving on average, sort of their average kinetic energy, and also the transfer of that energy via different mechanisms. And then finally, nuclear energy. Here I do show sort of the most stereotypical and dramatic example of that in terms of a nuclear explosion. But there's lots of different ways that energy from inside the atom manifests and can be studied. And as noted in the previous slide, we're going to be focusing in this series on mechanical energy, and there is plenty to talk about just with that. The word mechanical comes from the Greek word mechane. I don't know how to pronounce that, but the word itself, pretty cool, means device, tool, plan for accomplishing something, aka cunning. And we can actually look at mechanical energy from a couple of those perspectives. A lot of times we use tools to change the energy of objects. And if we consider energy to be the ability to cause change, you can almost think of change as the ability to accomplish something. So some nice tie-ins to the idea of energy when we use the word mechanical energy in this context. And we generally consider mechanical energy to be associated with physical forces, pushes, pulls, maybe even something that you might use with a hand tool, back to the definition of mechanic. And the sum of energies associated with an object's motion and position is considered mechanical energy. So within mechanical energy, there's a couple things that we're going to be taking a look at, and each of those are calculated in different ways. Okay, as we take our obligatory tea break, we can look at all the energy that's in play in this picture of Kermit here. Again, he's changing the potential energy of the glass by lifting it up. The glass has, I'm assuming, thermal energy associated with the tea, if it's a hot tea. You got radiant energy in the background from the sun. You can see a taxi or something moving in the background with some kinetic energy. It is chock full of energy. And I will be too as soon as I drink a little bit of tea. All right, moving on. So if mechanical energy consists of energy from motion and energy from position, we'll take a look at those each now. Energy of motion is known as kinetic energy, and the term kinetic shows up all over science. Greek word kinen is its sort of base root, and that means to move. And you could not pick a better base root than for kinetic energy. When an object's moving, it definitely can cause change. Think basically any sport in the world probably has moving objects associated with it. The real world interactions, one of the easiest ways to change something is to move something else into it with some sort of velocity. So definitely kinetic energy is a big, big part of our everyday existence. And when we are trying to change something using the motion of an object, you can increase that ability to cause change if the object moves faster. If I ram something into another object with more speed, even if it's the same object, I can cause it to change more. And also, if that object is more massive as it is moving, it has more ability to cause change. If you have a second grader on a skateboard and they slam into you, their ability to cause change to you is going to be much less than if it was a studio wrestler on the same skateboard at the same speed slamming into you. So mass is an important idea. And we can look at those relationships through a formula and start to see the details about how they each factor into that total. Examples of these formulas in play are going to come in later episodes, but for now, let's at least say hi to the formulas. Hello, kinetic energy. Kinetic energy sometimes is just written as a capital K or KE, as shown here. And the formula is equal to 1/2 mv squared. In this case, m stands for mass, and v is going to stand for the speed here, not the velocity. It doesn't really matter whether an object's moving east at 10 miles an hour or west at 10 miles an hour. It's going to have the same kinetic energy either way. So we don't have to worry about direction when we're using V in this context. And if you work out the units, units for mass, standard international system, mass is kilograms and speed is meters per second. If you square meters per second, you get meters squared per second squared. And rearranging that formula a little bit, you're going to end up with kilograms meters per second squared times meters. A kilogram meter per second squared is a Newton. And then you're left with one additional Newton as well. So energy can be talked about in terms of Newton meters. That relationship is going to come to be a little more important later in the series. And we can name it after a dead scientist, in this case, James Prescott Joule. Remember, when you're naming a unit after a scientist, you do not capitalize the unit when you write it out in full, but you do capitalize it when you write just the letter itself. So joules or capital J. And looking at this equation in a little more detail, that V squared term is important for a couple of reasons. First of all, because it's squared, it has a much larger impact on the overall kinetic energy than changing the mass by an equivalent amount. Again, that doesn't mean that mass isn't important. It just means that small changes in the speed can result in large changes in the kinetic energy of the object. In addition, we do square that speed. So I did talk about the idea that we don't worry about direction. This is just another indication that kinetic energy can never be negative. Mass can never be negative. And when you square a term, you're not going to get a negative answer. We're working with real numbers. So the lowest kinetic energy you can ever get is 0. Basically, kinetic energy exists or it doesn't. You can't. There's no direction associated with it. It's a magnitude value only, aka a scalar. And then its partner in crime for mechanical energy is potential energy. And potential energy comes from the Latin word potus. And potus, again, has a lot of definitions associated with it: powerful, able, capable, possible. And I think we should probably focus on the latter definitions for this one. Capable of or possible, I think, are great definitions to think about in terms of potential energy, because we basically think of potential energy as stored energy. Now, there are different ways that we can store energy, but it's energy that could be released at a future point, but is not necessarily going to be released. One very simple example of that is lifting an object up in a gravitational field. If I have a heavy object and I lift it up higher, it increases its ability to cause change. If you have a bowling ball and you have it 1 centimeter above the hood of your car, or if you have it 3 meters above the hood of your car, there's a really big difference there in its ability to cause change, its potential to cause change. And that's the version of potential energy that we're going to be focusing on in this introductory course. Another one you sometimes see in introductory courses is what's known as elastic potential energy, when you bend or deform the object. So think like a trampoline, think like a bow and arrow, or stretching a spring. That's often not too far off the path for new people learning physics, but we are not going to be discussing it, at least right now, in this series. So if we limit our considerations of energy to just gravitational potential energy at this point, we see that our equation is written as PE. I sometimes like to include the subscript G, just to emphasize we're talking about gravitational potential energy. Depending on your class, you might also see this nomenclature as a capital U. Sometimes we use that for potential energy as well. And it's equal to mass times the acceleration due to gravity times the height of the object. Height's a bit of a troublemaker here, because height is referred to with respect to a reference point, and we can get ourselves into a little bit of trouble here, because we can define that height in a lot of different ways and actually end up with different potential energies depending on where we define that point. The units actually work out to be the same. You can see it's kilograms times meters per second squared times meters. You smash that together, you get kilogram meters per second squared, which is a Newton, and then you have another meter, and there we have our term again, Newton meters, which is the same we had for kinetic energy, as well it should be. And Newton meters, again, can be written as joules. And if you're paying attention, you might note that there is the term mg in here, which is the idea of weight. So the object's potential energy, its potential energy, if you want to think about it that way, increases the heavier the object is. And we've talked about that idea of weight earlier in this course. And generally speaking, when we talk about just weight as a term, we don't necessarily include a negative sign in front of it. Again, if I say I weigh 195 pounds, I don't say I weigh negative 195 pounds. The implication is always there that the weight's going to be acting down towards the larger mass, whatever I'm on there. And again, in this case, we do not include the negative sign in front of the G. So I'm not saying the potential energy can't be negative. It can be, but it's not going to be negative as the result of the actions of the G, nor obviously can it be the result of the action of M. So if we do end up with a negative sign for potential energy, that is going to come from the height, and we're going to talk about that more again in a lesson. Now, just because there's a negative sign in front of it doesn't mean it's directional. So it's still a scalar quantity, energy you either have or you don't. But depending on how we define it, we could have positive or negative values of that. Okay, a quick closing thought or two. If you're taking a fairly stereotypically designed physics course, energy is not going to be the first thing that you're talking about. You probably have started with Newton's laws, but energy provides an interesting opportunity to revisit a lot of the scenarios that we talked about in terms of forces. And without forces and with energy, we can look at things like objects going up or down or rolling down ramps or interacting. And energy just provides us with another perspective, another opportunity to look at it. And by looking at it from a different way, we often can find solutions in a faster and more elegant way than forces allow us to. Not always. Sometimes forces are easier. But sometimes looking at it through the vantage point that energy provides is just a cleaner, faster way to solve problems. And sometimes I remember being a new physics student, I really appreciated what we could do with energy. I thought it was pretty cool what we were able to get done. So lots to look forward to, definitely. And happy to have you come along. All right. If energy is the ability to cause change, you have the ability to cause change right now through your actions. If you enjoyed learning about introductory energy topics, please consider liking the video. If you have any questions about what I talked about, leave a comment in the field below. And to keep informed on what's going on with transparent physics and to help the channel grow, please consider subscribing to the channel. And as we end another lesson looking over this star field ablaze with radiant energy, I'm always appreciative that you choose to come along with us on these lessons. I hope I've made introductory energy concepts a little clearer for you on this lesson from Transparent Physics.